Okay, by the end of this video you should be able to describe and explain concentration time graphs and rate time graphs in terms of the reactants of products concentration and the rates of the forward and reverse reactions. So we're going to explain it initially at the beginning as the reactions proceeding and then at equilibrium. So an equilibrium reaction is a reaction that's reversible. So that you could form products and then back to reactants. Definition: at equilibrium, the rate of the forward and reverse reactions is the same. So the concentration of the reactants and the products at equilibrium will remain constant, which doesn't mean that the reaction has stopped. The reactions are still going, so it's a dynamic equilibrium. Don't confuse this equal part of the equilibrium with the concentration of the reactants. The concentration of the reactants and products may be equal at the beginning, at equilibrium, but they don't have to be. You could have more reactants than products or more products than reactants. So it's not the concentration that's becoming equal, it's the rate that becomes equal. Alright. So it's good to be able to explain these diagrams together and understand how they work together. So we're doing it for nitrogen and this is a classic reaction. The nitrogen and hydrogen is forming ammonia. It's also got unusual, different mole ratio numbers, so 1 to 3 to 2, which is useful later on when we look at examples. Alright, so we're starting at the beginning. So pretend there are no lines drawn on this. We should be able to draw the lines. So for this particular reaction, we've started with 1 mole per litre of nitrogen and 3 moles per litre of hydrogen. So the exact mole ratio amounts. So initially there are no products, so you've got no ammonia to start with, only reactants. So the only reaction that's happening at the beginning is the forward reaction. Okay, so as the forward reaction proceeds, the concentration of the nitrogen and hydrogen decreases because there's collisions between the particles. The frequency of collisions between the nitrogen and hydrogen is the highest at the beginning because it's the highest concentration. So the rate of the forward reaction initially is the highest at the very beginning. And then as the concentration, as your particles collide, the concentration goes down, so the frequency of collisions goes down, so the rate will go down. These, because they're both reactants, they both go down or go up or whatever when we're analysing these later on. They'll both move in the same direction together. Alright, so now as the reaction's proceeding, you're forming product. So you're making ammonia, and some of the ammonia, if we looked at this to begin with, if this was just a forward reaction, an irreversible reaction, then your hydrogen and nitrogen should react together until there was no reactants left. So these lines should come right down to 0. And your ammonia would form until you've got 2 moles. With these particular amounts, you would get 2 moles per litre of ammonia. So the ammonia should, if it was irreversible, just going in the one direction, come up to here. So clearly something's happening because you get to a point where you don't lose any more reactants or make any more products. So the reason is that your ammonia molecules, some of them are getting together to turn back into nitrogen and hydrogen, reform nitrogen and hydrogen. So you're getting the reverse reaction is happening as well. So that's the equilibrium symbol. And you must include that if you're asked to write an equilibrium reaction. Okay, so we're looking at the reverse reaction now. So concentration is low to start with, so the rate of the back reaction is low. And then the concentration, as the concentration increases, the rate, this is the y-axis is rate, so the rate of the back reaction is increasing. So when you're writing explanations for this, always start with your concentration. As the concentration of the ammonia increases, the frequency of collisions between ammonia molecules will increase, so the rate of the reverse reaction increases. So you notice that the concentration of these is going down, the rate of this is going down. The concentration of this is going up, the rate of this is going up. So these two, the forward and the back, this is fast and then slowing, this is slow and then speeding up. Eventually they both become the same rate. Once you're forming ammonia and breaking it apart at the same rate, then you're not making any more product or losing any more reactants. And so from this time on, you're at equilibrium. So these straight parts of the graph are equilibrium. Okay, equilibrium is reached when the rate of the forward and reverse reactions is the same, so the concentration, your explanation always needs to start with concentration. Concentration of the reactants goes down, so the rate of the forward reaction goes down. Concentration of the products goes up, so the rate of the reverse reaction goes up, until the rates are the same.